I'm extremely happy to introduce Colijn, who used to be in Boston with us and now, through Bristol, has arrived at Imperial College.
Thank you. Thanks to the organizers for inviting me. It's great to be back in Boston and to see many of you again, and many of you for the first time. It's interesting. I think that modeling is important, and I will try to make the case that modeling TB is interesting and important, but after these two rather frightening talks, I'm struck with how little modeling can offer in some of with respect to some of the problems that you've just heard about. When I was preparing this, I was sort of reflecting on why there haven't been that many good modeling papers, or really any modeling papers, released in the past few years for TB. And I was thinking, well, I haven't written any in the past year or two. Well, there's one, but not too many either. And it's just really hard. So I thought I'd give some introduction at some of the factors that make TB modeling a really challenging thing to try to do. Of course, you can make up models. It's just getting something useful out of them that's particularly hard. I'll discuss a few models to date, and I'll give some of my thoughts on what's next. Obviously, it would be great to hear from you what you think of that in the next discussion. So I want to kind of talk a bit about individual level complexities of TB models and also population level complexities. And I've just sort of sketched out a few, and this is by no means an exhaustive list of the things that are complicated about TB that are not necessarily as complicated in some other pathogens. So I think probably at the top of the list is the question of progression from latency to active disease. So as you probably know, upon initial infection, there's sort of an elevated risk of progression to active TB over the first few years, maybe 5 years. And then latency can actually last a very long time, and the sort of standard wisdom is that only 10% of people infected with standard sort of drug-sensitive TB would progress to active TB disease over the course of their lifetime. So this latency can last 50 years. But then can reactivate. And so it's not clear how large a part that plays in TB, at least it's not clear to me, but probably not too much compared to sort of the fast progression within the first few years. But what causes that progression and with which strain one progresses and how long that latency is going to last, whether it's months or years or many years, that's unknown, and those are very, very sensitive points in most of the TB models that we've developed. So those rates of progression, and even a rate is a very simplified way to look at the very complicated immunological dynamics. But those rates are very, very hard to determine empirically and play a huge role in determining what the prevalence and incidence levels that the models predict are going to be. So that's sort of probably the major point. I'm going to try to get this button thing the right way around. I did it. Okay, so that's probably, I would say, is the top thing from a modeler point of view about what makes TB modeling challenging. You've just heard a lot about treatment and how important it is, and of course, it's clear that treatment is going to be important, and you've just heard a lot of very interesting comments about how the sort of details of treatment. Those are quite hard to incorporate in a standard kind of SIR type model because of the time frames, the individual level complexities. Of course, the interaction between sensitive resistant strains, which types of drug resistance, the dynamics of acquisition of drug resistance on treatment and different treatment regimens, co-infection, and we've worked a bit on that, and I know Ted Cohen's quite interested in that, so that's been one of our focal points of modeling, so I'll talk a bit about that. That, of course, is really interesting, and it's really important to the dynamics of models. So, and then, of course, that's a huge one, co-infection with HIV, which brings in HIV transmission dynamics. So those are all, not exclusive to the individual level, but those are all factors that I would say make TB modeling hard in terms of individuals in TB models. And then there is, of course, a set of complicating factors at the population level, including contact structure and who is infecting whom, and whether it's really good mixing or is transmission a lot at sort of household level, nosocomial transmission, or social settings, or all of the above, and so that's a factor. That's a factor. Surveillance questions, which we heard about yesterday, are of course a huge question in driving not only modeling choices, but everything else. Reinfection is another one where we've developed some models that I do think this interacts with the question of progression from latency to active disease in potentially very important ways. And of course, circulating strains, and then HIV contact structure is another one, because as you've heard, HIV co-infection is to a large extent driving dramatic increases in TB rates. So if you ask the question, how are we going to bother with modeling any of this, and if so, how? These are all, in a sense, huge points that affect modeling choices, and modeling choices in turn affect the results that you would get from models. So you might at this point be thinking, okay, well, why would you bother modeling any of this, given how complicated it is and how likely you are to have a model that's not only wrong, but wrong and not useful? I think that all models are wrong, and hopefully some are useful. I guess from my point of view, the motivation is strong because the problems are so bad. And models are pretty cheap, and if we can make useful models, it's nice to do that. So what I'll talk about is a few models that have aimed to look at sort of central questions on one or two of these blobs of complexity. I'm really not of the belief that you can make one big meta model that has all of this stuff in it and then ask it to really do anything useful, because it's going to be not only wrong, but incredibly complicated and very difficult to analyze and understand. So our approach has really been to take one or two of these things and form simple questions and try to use relatively simple models to answer them. So I'll talk about a model that Ted and Megan and I did with a probabilist at the University of Bristol on the very simple question. I would categorize it, is there like a page up? I would categorize it within this particular little ball of acquisition, and it's even a very simple model of that. So the question is how multiple resistance emerges in the first place. And you've already heard some about that basically this can emerge through sequential effective monotherapy. But under good treatment, and of course, you're not going to believe me after hearing the two talks you just heard, but it should be very unlikely under good, well-implemented standard regimens, and it seems to have emerged a lot. So we looked at a model, a mathematical model, in which each bug divides. Each time it divides, it has very small probability of a single-point mutation conferring resistance to isoniazid or rifampicin. And then the descendants, so let's say that one happens and you get a single mutant. Those descendants also divide, and each time they divide, they have a probability that they get a further resistance mutation. So this is probably pretty standard. The standard calculation that you see in a lot of TB papers is this, and I've missed out a big capital N here. So imagine that where the red dot is, there's a big capital N for the population size of the bacterium within the host. And you would have the probability that you would see dual resistance upon reaching a clinical detection size of like 10 to the 9th or 10 to the 10th bacterial cells, would be the probability of the first kind times the probability of the second kind. And that would be, for our best estimates of INH and RIF resistance, 10 to the minus 18. So even if you had 10 to the 10th cells, you would still only have a 10 to the minus 8th probability of resistance. You see this all over the place, and it's actually wrong because that's the probability that if you have 10 to the 10th cells, you'll see dual resistance in one generation, like after one cell division. So that doesn't account for the fact that if one happened early, it would have lots of descendants that have accrued until this time. So if you take that into account, and we did a slightly more complicated thing involving death rates and growth rates. You can show that pre-existing dual resistance, this is prior to treatment, completely sensitive, is rare, but it's not all that rare. It's instead of 10 to the minus 8th, it's 10 to the minus 4. And it goes up with the relative fitness of the resistant mutants. And furthermore, these numbers are immensely variable. So this box plot shows the numbers of single mutants at detection size. And this is what was referred to yesterday as sort of standing variation that you expect if you've thought about these things before. They're really, really variable and can really vary by 2 or 3 orders of magnitude. So that's a probabilistic model that doesn't really even encapsulate the true complexities of the dynamics of acquisition of resistance, because this is even pre-treatment. We looked at some treatment models too, and of course these probabilities go up if you then apply sequential monotherapy, because you have pre-existing high numbers of pretty much every single resistant mutant before detection size. Okay, but that's one model that attempts to look at one aspect of complexity and individual level complexity in TB. I'm going to move to the population level. This is a model. I mentioned co-infection, and this was one thing that has come up a number of times about in pneumococcus, and I guess also in staph, about what is it that is driving the continued coexistence of multiple variants. And so we just saw with the TB composition in South Africa that there really are multiple different lineages of TB, and also obviously circulating drug-resistant and drug-sensitive types. So given that, sort of from the modeling point of view, TB has, you can be susceptible, and then it enters this latent asymptomatic and uninfectious stage, and then later subsequently possibly progresses to an infectious stage. And we see mixed infection. I haven't even drawn it here because it isn't in this model, but we see mixed infection, and we know that people who are exposed to one strain may be exposed subsequently to another strain. That leads, from a modeling point of view, to ask, okay, well, what's happening? Are they then mixed together in a latent stage? Does the new one not have a latent stage and go straight to infectious, or do they outcompete each other and just, latency of one turns into latency of another? And since we can't really measure what people are infected with in latency, or indeed whether they're latently infected at all in some cases, we just don't know. So models are a convenient way to explore simple questions about what happens. And then the result, I won't go into the details, but the result is that co-infection matters. It can significantly change the long-term outcome. So, for example, in this picture, the resistant transmission parameter is shown along this axis, and the sensitive transmission parameter is shown along that axis, both proportional to R naught. So if they're both small enough, you have no disease at all. Because of acquisition, if the sensitive parameter is really high, you have mostly sensitive disease with a little bit of resistance through acquisition. If the resistant strain is transmissible, and if it's really transmissible, it can sort of take over, or you can have this coexistence. And we studied what happens if you have isoniazid preventative therapy given to people in this class, and it then selects for resistance at the individual level, at the latent stage. And co-infection makes a difference in terms of providing essentially a reservoir for the resistant strain, so that resistance can effectively succeed more than it would have otherwise, and it can expand the region of parameter space where you would expect a resistant strain to take over. So far, resistant strains haven't really taken over, but the take-home message here is that co-infection that you can't observe in this funny latent way, whether it's mixed or not, can actually have a big effect on the long-term population dynamics of simple models. And that also works in somewhat less simple models. This is a model developed by Renat, who's here in the audience. It includes co-infection and active disease and slightly more detail, and we sort of see the same effect of co-infection, where a resistant strain can persist where it would otherwise be eliminated. But of course, as you saw on the first slide, these simple models don't have lots of things in them, and here's a list of some of the things that these simple models didn't have. They didn't have HIV, mine didn't have mixed active infection, they didn't really have treatment, they didn't really have recovery, they didn't really have treatment failures, they didn't really have relapse, and there was a whole bunch of stuff that isn't really in here. They didn't really have MDR, XDR, different classes of drug resistance, we just had resistant or not. And there's a table in the way there, but as you can see, this just even if you did all of this, and you put in HIV and you put in a treated class and you put in relapse and you put in, tried to put in a rate of treatment failure and you put in mixed active infection, you'd get a sort of a box dynamic like this. You would still only have a 2-compartment model for HIV, negative and positive. And that's not right, because HIV has different stages and varying infectiousness and time since infection and all kinds of things, not to mention antiretrovirals. So the point is, these models get really complicated really fast. They have big limitations. Also, they don't answer some of the questions we really want to know, which is sort of at the population level, what would be the effects of some of the things that Helen was proposing that we really need. So reduced delays to treatment, reduced delays to diagnostics, improved timing, different types of acquisition treatment regimens. So they're sort of poor for, ODE models are poor for doing all these things that we want. They're poor for outbreaks, they're poor for individual factors, and they're poor for some population level outcomes because of these facts. Except for gaining fairly general insights, namely, co-infection's important and these kinds of things. Okay, I'll talk a little bit about contact structure. I have a very talented PhD student, who's done a nice model of 2 different networks. I talked a bit about HIV, and it obviously spreads on a sexual network of contacts, whereas TB spreads on a network of respiratory contacts. And of course, as you've heard, allusions to these diseases interact. Well, in particular, I guess HIV interacts with TB. Neither network is really randomly configured, and so what we wanted to know was, given that isoniazid preventative therapy is being rolled out in some settings and is given to HIV-positive individuals who are suspected to have latent TB or a risk for latent TB, to prevent their progression to active disease, can we say anything about the network effects and whether subsequent reinfection would really undermine IPT at the community level, even though at the individual level it seems very effective? And the answer is essentially yes, but it's complicated. So we had a model in which each infection spreads over its corresponding network. Isoniazid preventative therapy was given. We asked, is it undermined by reinfection? And the answer is sometimes. In particular, you can have sort of a local network. It actually looks quite a lot like the network of hospitals, but that's sort of beside the point. If you drew out the network, you can see these sort of pockets of very high levels of reinfection. And if it's not so local, then it's more spread out. So that's fair enough. If you've done spatial modeling, that won't come as a surprise that you can make a network that's very local or one that's not, and you see this. What happens is that IPT can be fantastic in networks like this, because it can be the case that the burden of TB is sufficiently clustered among HIV-positive individuals that you really just eliminate it that IPT can effectively eliminate TB in these little pockets. Or it can be the case that if you don't do quite enough IPT, or if there's a burden of TB outside of the individuals that you're treating, that subsequent reinfection really will undermine IPT. So the results are highly variable in these cases. And the results are not so variable and really quite good. IPT looks great in these kinds of cases where it's not so likely that someone prevented from progression will, 2 years subsequent to that, just be reinfected and progress again. So that's sort of network modeling. The same student is currently working on models using much simpler math, so not full simulations. Well, the math is maybe not simpler, but the models are simpler. Not full simulations, not full time-dependent solutions to big ODEs, but just simple models to look at very short-term predictions of outbreak size based on who's in the population and their risks of infecting others with the various types. So the model, you could sort of schematically illustrate it like this, where you imagine the infection sort of taking a random walk through a network of different types of individuals. And she's got a framework, we haven't yet applied it to XDR-TB, but we're going to, of just generating sort of expected outbreak size and maybe a variance around that with respect to parameters in the style of R naught, sort of R effective. Okay, so I'll talk about what I think should be next in TB modeling. And you've noticed I haven't really talked about any data. So I think what's next, it would be great to have some data. That would be really good. Not that, I mean, I don't want to be completely facetious, because it's not that our models haven't been underpinned by any reality whatsoever, but the kind of classic data, incidence numbers, prevalence numbers, they're really too limited to define the models with the complexity that I described. People tend to just use other people's model parameters, which is a little bit weak. We're hoping that by changing the kinds of models we use to the more sort of probabilistic, less demanding of data kinds of models, and at the same time making use of new data, that we'll be able to link models and data a little bit more strongly. So I guess the take-home message here is that, in my view, TB modeling is pretty complicated and pretty fraught, and can be very frustrating. Of course, the goal is to extrapolate some of the individual level complexity to the population level, and of course then hope to figure out better things to do to control TB. And it would be better if models could be better linked to data without becoming not only wrong, but not useful. All right, thank you.